A few hints on homework problem number 6 here for you. Problem number 6 discusses a dipole that's oriented along the y-axis. So here's the dipole right here. There's a plus charge here and a minus charge here, and there's 1 centimeters between them. Other information that's given in the problem then is that there's a point 10 centimeters above the center of the dipole. So if you take a line that sort of bisects the dipole and you go up 10 centimeters above it, this distance right here, the electric field at this point is 360 newtons per coulomb. That's how strong the electric field is. Now you might guess that the electric field at this point has something to do with the amount of charge here and the amount of charge here, and indeed it does, and that's exactly what you're trying to find in this problem. How much charge would have to be here and here, equal and opposite, to deliver an electric field of 360 newtons per coulomb, 10 centimeters above the dipole. That's what part A is about. Part B wants you to find the electric field way over here at this point right here, so not above the dipole, but on a line sort of out here on the x-axis right here. I'd like you to find what this electric field would be. Seems like it would be possible to do that if you knew how much charge was here and here, and indeed that's how the problem is going to work. You use the 360 newtons per coulomb in part A to find out how much charge is here and here, then you take that charge into part B and compute what the electric field would be right there. In order to get this problem to hash out then, you just need to be familiar with 2 results of the dipole that we know about from the lecture. The first one is this formula right here. It's sort of labeled EY perpendicular. Now the reason why it has all of these labels on there is because in the first case here, it refers to a perpendicular line. And by perpendicular line, I mean a line that's perpendicular to the axis of the dipole. So here's the axis of the dipole right here, and there's an axis right here that goes out which is perpendicular to the axis. That's what this perpendicular calls for in this particular formula here. The other part about the formula is this perpendicular line must bisect the dipole. So this line must be perpendicular to the axis of the dipole and must be equally spaced on this side and this side. It must bisect the dipole. That's the only case where this formula is valid. It's pretty simple and limited in use, but it's all we can sort of get at analytically in the lecture, so we go ahead and use it. The reason why it's EY is because the electric field at this point on a perpendicular bisected dipole points down in the y direction, EY like that, so that's why it's called E sub y. That's what this means. And the formula is given by these symbols that you see here. K is the electric constant, Q is either the charge here or here, equal and opposite amounts. S is the distance between the two charges, both here and here, and X is how far you are away along that perpendicular line that bisects the dipole. So X indeed would be this distance right here that goes from the axis of the dipole out to the point in question. So you could use this formula here to answer part B of this question if you just knew what Q was. And I'll tell you how to find Q now. You find Q by looking at part A in the problem and using this 360 Newton per Coulomb electric field. How do you do that? Well, the second formula right here is the result we got for the electric field above a dipole. So we're not talking about a perpendicular bisector, we're talking about above the dipole on the axis of the dipole here. So we have to emphasize this formula here also applies to on the axis. Now you can either be above or below the dipole, but in this case we'll be above. So we know if we go 10 centimeters above the dipole as called for in the problem here, we'll get a 360 Newton per Coulomb electric field. So the way we can definitely start this problem, say, okay, look, I'm going to get the 360 Newton per Coulomb field, and that's exactly what EYA is equal to. So if you plug the 360 newtons per Coulomb in for this parameter right here, you know what Y is, you're 10 centimeters above the dipole. You know what S is, that's the dipole spacing. That's the 1 centimeter in there. Seems like you can solve for everything in this problem here and just get Q to come out. You can get Q equals to some number from this problem. Okay? That's what will come out. Once you have Q then, you can use this Q for part B, where you can use the EY perpendicular formula to compute the electric field out here at this point, given the Q that you found in part A. So that's sort of the plan on this problem here. You have to recognize there's 2 different formulas for the dipole, one on a perpendicular bisector, the other one either above and below. This problem wants you to use and exercise both of them.